Hi, my name is Tim Yammer and welcome to my presentation about the scalability of different OpenMP implementations. So I think you might be familiar with OpenMP to some degree, as it is one of the most commonly used ways to achieve parallelism inside one node. Newer systems offer much higher degrees of parallelism, but not only in terms of the number of nodes, also they often provide more and more cores per node. Therefore, utilizing the parallelism inside a single node as efficiently as possible is a critical component in order to achieve maximum performance. And in previous work we discovered that there are some scalability issues with OpenMP runtimes, but we did not investigate the reasons for the scalability differences of different implementations so far. So in this talk we want to analyze the impact of different implementation choices made and the system architecture on the scalability of the different implementations. We are curious if the previously detected scalability problems are still relevant today, and maybe we could learn something from the different implementation approaches that are taken by different implementations of the OpenMP standard. And also we are curious if we can see the impact of the system architecture. Because modern CPUs are available that do not offer a core count that is an exact power of 2 anymore. For example, you can buy CPUs that have 6 or 12 cores available. And as you can see in this picture, this might lead to a somewhat asymmetric internal CPU structure. And we are curious if we can see the impact of this internal structure on the scalability of OpenMP. So the outline of this presentation is quite straightforward. I briefly want to introduce you to our experimental setup and then talk through a selected list of OpenMP constructs. For the full list of constructs that we've analyzed in our study, please refer to our paper. So we conducted our experiments on the Lichtenberg high-performance computer here at the TU Darmstadt, and actually we used the old Lichtenberg system, not the new one that have entered the top 500 at place 93 on this ISC. As we want to have access to the source code because we want to compare the different implementation choices made, we will compare the most commonly used open source implementation of the OpenMP standard, that is the GNU implementation that is used in the GCC compilers, and the Clang and the LLVM implementation that is used in the Clang compilers. We will use the system default version at the time of our study. Of course, we need to take care about the thread placement, and we'll use the OpenMP provided environment variables to do this. And the only thing that we need to do to our data before we can show it to you is that we cut the top 10% of our measured timings. This is because we want to filter out the noise where the operating system interrupts the process for some reason. So let's get right into it and talk about the performance of the different implementations of OpenMP. Here you see at the x-axis the number of threads, and the y-axis depicts the overhead. And the overhead in this case for the single clause is the time that the threads that do not actually process the single region, these threads spend within the single region. So what we do is we take a timestamp, and then comes the single region, and then another timestamp. And basically between those two timestamps, the time should be basically 0, so as low as possible. At least for the threads that just skip the single region, as we have specified in no wait clause, and there is no implicit barrier. So if you compare the left hand figure to the right hand figure, you see that on the left side we utilize a closed thread binding, and on the right side we utilize a spread thread binding. But the general trend behind these two figures is the same. So you see that for the GNU implementation, the overhead rises quite linearly in this case, while the overhead for the LLVM implementation stays roughly the same. And this is the same for the closed thread binding. But if you look very closely, here you can see a 12 or 18 thread, there is a rise in the overhead for the GNU implementation. And this is because our system is organized into 4 NUMA nodes with 6 cores each. So if the next thread is placed on the next NUMA node at 12 or at 18 threads, then you can see the impact of this. This is why we will utilize the closed thread binding for the rest of this presentation. So here we see that for the GNU implementation the overhead rises, while it stays roughly the same for the LLVM implementation. And the key thing is, of course, why is this the case? So is the LLVM implementation really superior to the GNU implementation? So let's have a look into the source code. The general idea behind these two implementations is the same. So you have a single counter that counts the number of single regions encountered so far, and each thread has its local counter, and it is incremented whenever a single region is encountered. And then there is a team's single counter. And so this compare and swap operation tries to increment the team's shared counter. So the first thread that arrives at this code block will increment its local counter, and then increments the shared team counter. And the second thread that arrives will increment its local counter and then cannot increment the shared team counter as it has been incremented by another thread so far. So the first thread that arrives will increment the counter and then process the single region, and the other will fail to increment that counter and will then skip the single region. And this is also the idea that is behind the LLVM implementation. So you have a thread local counter that counts the number of single regions encountered. It will be incremented the same as for the GNU implementation. And then you spot the difference here. First, there is a non-atomic compare operation. And then you have the atomic operation, which is the same as for the GNU implementation. The team's counter should be incremented. So there is an addition of this non-atomic compare operation. What happens in the LLVM implementation is that not every thread issues an atomic operation. Only if it spots an opportunity to increment that counter, only then an atomic operation is needed. Otherwise, it will just skip the atomic operation. And this will lead to less congestion. And this is the reason why there is with more and more threads, there is more and more congestion in the GNU implementation, but this is not the case for the LLVM implementation, because this non-atomic compare operation does not create congestion. So in this case, we could learn from the GNU from the LLVM implementation that we could use less atomic operation. And in this particular case, the addition of this one non-atomic compare operation does not hurt performance. Yeah, actually, it is beneficial to performance, as you've seen. So let's have another look at the barrier implementation. Here you see again the number of threads versus the overhead. The overhead in this case is the time between the last thread arriving at the barrier and the last thread leaving the barrier, because this is the time that at least one thread spends processing the barrier operation, although this is not needed by the semantics of the barrier operation. Because once the final last thread has arrived at the barrier operation, then all thread should resume to the user code as fast as possible. Here, between the left hand and the right hand figure, the distinction is in the order that the threads enter the barrier. So on the right hand side, we have a synchronized thread order, which means that all threads arrive at the barrier at roughly the same time point. In contrast, on the left hand side, we see a random thread ordering. This means that each thread has that we have a time frame, and each thread uniformly at random picks a time point within this time frame and enters the barrier at that time point. So there is a small delay between the thread entering. And we can have a look that the GNU implementation's overhead rises quite linearly, so I suspect there might be a linear scheme behind that. And you see that the LLVM implementation's overhead has a logarithmic curve, so I suspect there might be a logarithmic scheme behind that. So let's have a look at the scheme behind that, and indeed LLVM utilizes a tree-like scheme while GNU utilizes a single shared counter. But apparently the GNU implementation, as you can see, the GNU implementation works very well if there is a small delay between the threads arriving at the barrier. So imagine that thread 0 is the last thread arriving at the barrier. The only thing that thread 0 has to do in this case is it has to increment the counter by 1, and then all threads can proceed with the section after the barrier. In contrast, in the LLVM implementation, what the final thread that arrives at the barrier has to do, it has to process the whole tree in order to gather that all other threads have also arrived at the barrier. And therefore, the work done by threads 1, 2, and 3 in this case, they can be somewhat shadowed by the application's load imbalance. As the thread 1, 2, and 3 in this example has to wait for thread 0 to arrive anyway, they could do some of the work needed in order to gather that all threads already have reached the barrier. So in this case, we could learn from the GNU implementation that some of the overhead needed in order to perform this barrier operation, some of these overhead can be shadowed by the application's load imbalance. The thread have to wait for the final thread to arrive anyway, so they can do some of the work that is needed in order to perform the barrier operation. But we could also learn from the LLVM implementation that a logarithmic scheme works better with a higher number of threads. Of course, the overhead only grows logarithmically in terms of the number of threads, and with more and more threads, this shadowing of the overhead in GNU is not sufficient anymore. So at some point, the application's induced load imbalance is not enough in order to shadow the higher overhead that is needed in order to perform this linear scheme. So in this case, there is no single implementation superior in all cases. Let's have another look at the reduction operation. Again, you see the number of threads versus the time needed to perform the reduction operation. And as you can see, you have this linear linear rise of the overhead in the GNU implementation, and there is a logarithmic curve in the LLVM implementation. And if you then look into the source code, this is indeed what happens. GNU utilizes a linear scheme, meaning that each thread writes its value to an array, and then the master performs the reduction of this join barrier. And in the LLVM implementation, the reduction is organized in such a way in accordance to the join barrier, which is a tree scheme. So one thing that we note is, here we plotted the cache misses of the reduction operation. And we note that the GNU implementation does not have a lot of cache misses. Basically, first each thread writes their local value into an array, and then there are some cache misses when the master threads collects the results. In contrast, the LLVM implementation, the tree scheme, have a lot of cache misses. But what we see, and what's very interesting, is if you look at 12 or 18 threads, then there is no steep rise in cache misses, as one might expect. And because we utilize one additional NUMA node, but this does not increase the number of cache misses. So we do not see that the structure of the reduction operation is aligned with our system structure, for example, with the different NUMA nodes. This is not the case. One particularly interesting thing to note is that if we stay inside a single NUMA node, the very simple approach of the GNU implementation is very performant. Here you see that at 4 thread, for example, you need to introduce another tree layer if you want to have the 5th thread. The LLVM implementation needs to introduce a tree layer, and this is not needed in the GNU implementation. So in this case, we could learn from the GNU implementation that this linear approach has less overhead for a low number of threads. It might even be possible to vectorize the reduction operation in these cases. In contrast, it is not possible to vectorize a logarithmic scheme, a tree scheme. But this logarithmic scheme works better with a higher amount of threads, of course. So here it might be a good idea in order to combine these two implementations, where, for example, first a GNU-like linear approach is used in order to reduce the values inside a single NUMA node, and then we utilize a tree scheme in order to combine the values from the different NUMA node. So in summary, there is no implementation that works best in all cases. In general, you could say that the LLVM often utilizes logarithmic approaches, and this works better with higher thread counts. But the GNU implementation often utilizes a simpler linear approach, but this works better with lower thread counts as there is less overhead introduced in some cases. Previous work already suggested the usage of so-called adaptive implementation, which means that an implementation might be able to adapt in regards to the number of threads. For example, we want to utilize a GNU-like linear scheme and then switch to an LLVM-like logarithmic scheme once a sufficient number of threads is used. Also, it might be beneficial to adapt in regards to the system layout, for example, first reducing the values inside a single NUMA node and then reducing the values between the NUMA node. But we did not find such a behavior in our study, so therefore we think that there is still room for improvement in this area. And with this, I want to thank you for your attention.